Hello and welcome. Here we are in lecture 4. So we're going to pick up right where we left off last week. If you remember on Friday, we covered how to implement combinational logic in Chisel, right? So with combinational logic, we're basically able to make any kind of, mathematical, logical function we can think of in hardware, right? So I deliberately use that keyword function because it is a pure function, right? That is that hardware component is what it produces will always be a direct function of its inputs, right? There'll be no ability to kind of have the same inputs cause different outputs. No, the same input always causes the same output. So if you want to have any differentiation, you're going to need to be a little bit different. Okay, we had a concern about audio. I'm going to quickly double check that. Can anyone else confirm the audio? Okay, I'll keep going. Um, so yes, so the power blocks we built were purely whenever you get the same input, you always get the same output, right? But we know from hardware design, there's plenty of times we want to have hardware circuits to remember things, right? That is, they can have different behavior depending on what they've seen in the past, right? So in order to do that, you need to have state, you need to have some sort of memory internally, and refer to this broad category of hardware circuits as sequential circuits. That is, hardware circuits that um, can do that kind of stuff. So that's what we're going to cover today, right? We're on Friday. We kind of had, Chisel. Now we're kind of making combinational circuits. Today we're going to go ahead and add state to them. And then the coming lectures and keep kind of layering on more and more nice features. But, after today's lecture, for those of you who've taken a hardware design class, perhaps like CSC 100 at Santa Cruz, which is your kind of intro Verilog, FPGA kind of logic design course, basically everything you can do in that course, you will now be able to do in Chisel. And then some, already after just a couple of lectures, right? So it kind of shows you kind of power of this language, what we can get done. So, more concretely, what are we going to be talking about today? Well, number one, registers. That's kind of the most common, building block we use to remember things inside of hardware design. Next, of course, we'll cover just more general examples of it using, build sequential blocks. Then, of course, we'll talk about state machines or finite state machines and how we might use those in Chisel. And finally, show a little bit of kind of the tools of the trade, how we can do things to view simulation results, right? So we can kind of see how things work out. Okay, so as always, let's go ahead and load in our, notebooks. And as I always kind of point out, you can go ahead and play these notebooks yourself during lecture or take notes in these notebooks. You can launch a binary instance from that link in the webpage and don't even need to install anything. You can play with the code while I'm talking. So first off, let's talk about registers. So now, of course, a register, remember on the right, that's this box over here, the triangle, right? This triangle tells us a positive edge-triggered flip-flop. In other words, whenever the clock, once per cycle, we'll take the input, and that becomes the output. And for the remainder of that cycle, I can change this input however I want, but the output won't change until the next clock cycle, in which case, it changes again, right? So this register here is going to hold the state. Now, some register, every cycle takes this input and makes this output, right? Once per cycle. In practice, that's maybe a little bit too simple. And so we kind of usually add more things onto it to make it more kind of useful, right? And so, for example, you might want to have things like the ability to reset your register, right? Where you want to have, if reset is true, you want to load a certain value into it. Or perhaps, you don't want the register to change value if the write enable is low. And if you want to be able to turn off whether or not updates are possible on the register, you have this write enable signal, right? So the kind of capture, or as a kind of a reminder of the semantics of those kind of signals, I've made this little diagram here, which kind of shows behaviorally what is going on, right? So we have a register we're trying to set, we're going to set to value next, potentially, right? So what's the potential part? Well, you can imagine under the hood, this isn't quite how it's done, but you can imagine there's a mux, well, if the write enable is on, then yes, the next could become the next value register. If the write enable is off, we're going to take the old value, right? We're not going to change values, right? That's the, 0 in here, selecting the mux, taking the old way. Going a step further, right? Well, do I want to reset to a known value? If so, if reset is 1, doesn't matter what was in the thing before, doesn't matter what else the input had. I'm going to set this initial value, right, in it. Okay. And then perhaps reset 0, in which case we'll then have a chance for this to come through. So you can kind of see how to have this capability of having a register, sometimes you might hear me call it a flip-flop, that is able to be reset as well as has a write enable. Under the hood, you can figure it out like 2 muxes, right? And That's kind of a good starting point. Okay, so then what else is going on here? Well, you notice I colored clock and reset in green. The reason why is that those signals are implicit in chisel. So 98% of the time or whatever, you need to think about them or write them down. It gets passed around between modules. It connects to your registers and such. It's great. If there's ever a time when you want to, very much change who gets which reset signal or change which clock you want to use, that's totally doable. There's additional functionalities in the language to handle that. But when it comes to instantiating a register in Chisel, it's actually pretty nice and simple, right? Where you can really just instantiate, hey, I want this hardware block. I want a register, right? And this is in contrast from typical Verilog use where you don't actually say you want a register. You instead describe some behavior and you're counting on the CAD tools to infer that should be solved with register, right? You want it to be synthesized, right? And so that's already kind of a layer of indirection and a little bit of guesswork. And veteran Verilog engineers kind of know certain patterns the way to write their code that guarantees the tools will infer and synthesize that register, right? But rather than doing that approach, taking a very explicit approach, hey, I want a register, boom, here's another hardware block. And once again, it's kind of a reminder of how we're doing things with Chisel, right? Is that the way to think of Chisel is it's a program that is instantiating hardware components and then connecting them together. So if I want a register, I need to instantiate it and then connect its input and its output. And then the clock and reset, those will be handled under the covers. So I think I saw a question come in chat asking, wait, is this whole diagram the register? Good question. Technically, I might argue that just this portion on the right is the register. However, if we're being a little bit fuzzy with terminology, having registers that have the capability to be reset or the capability to have a write enable is very common. So perhaps, yes, you could think of this entire thing as being a very deluxe register, right? Of having, the ability to have a write enable as well as a reset signal that kind of controls functionalities. So instead of just being, an input and an output as well as a clock, it's an input for the data, it's an input for the write enable, it's an input for the reset, it's an input for the clock, and then an output for the value, right? So yes, you can think of this as kind of a deluxe register, and depending on what you're doing your hardware design, you'll see in the next slide, you may not necessarily need all these extra bells and whistles. So yeah, let's get right to that, right? So when it comes to register in Chisel, or reg for short when you instantiate it, as I said, you just instantiate it, right? You say, hey, I want a register. You need to give it a type. That's how the tools know how big to make it. So for example, you can say, yes, it's a bool. Okay, so it's a 1-bit thing. So yes, at this point, it's declared a 1-bit register. And this is a, Chisel logic floating. We have a Scala reference to it in case you want to point to it later on, right? But think about it as a piece of hardware. Okay, we have a register. Okay, well, we connect the register R by putting on the left side. Remember, this is kind of like, saying the input to R gets the output from what's over here, right? It's the connect operation semantics, right? So, well, I out it in. Okay, so that's the thing coming into our module, taking that to the input register, great. And then connecting the output register, right? The output to the input, right? Right to left, kind of the way you think of these things. To the output, right? So really all we've done was we built a tiny little module. It's just a single register inside of it. And so if I go ahead and try to view the Verilog for this, it's a little bit crowded. There's a lot of stuff that Chisel emits here that makes it nice for simulation, to do things for like randomization, for testing and stuff. But if you look past all this other junk and kind of look at the key internals, what do you see? Well, you see we have a register, right? And so one of the things that drives me bad about Verilog is they have this keyword reg, which you might think means register. That would be a very reasonable assumption. It does not mean that, right? It's just another language construct. Depending on how it's used and how the CAD tools interpret it, it either may or may not turn to register, depending on how you use it. This is one of the canonical ways of inferring register in Verilog, where you do an always block. Once again, Verilog's not the point of this course, but the reason why I showed a snippet is to kind of point out that yes, I built a simple register inside this module that, its input is IO in and its output is attached to the output of the entire module. Okay, cool. Maybe I'll pause here if there's any questions otherwise so far. Yes. So the question is, can you talk more about the functionality of the intended module? Yes, the functionality is just it's a module. Its only internals is a single register. And yes, input comes in to the register, and then it's passed out in the output. So it's just a single register kind of wrapped with a module wrapped around it. So maybe perhaps a better way for me to explain all this is that you can instantiate chisel objects outside of a module. You kind of need to have a module kind of enclosing context for them. And so for these tiny snippets in the lecture, I'm actually basically forced to have these modules, right? So, you wouldn't have a module just simple in real hardware, but yes, I'm using a module here just to kind of have a context for it, and I can take advantage of that situation to kind of very carefully label what I'm working with, right? I can label, hey, these are inputs, these are outputs, etc. But yes, it's just a single register inside of a module is kind of what we're working with here. And so, yes, so initially, that's all we have. It's a single vanilla, very stripped down register that takes the input in, spits it back out, and remember the output only changes once per cycle. But there's convenience features, right? So as I said, depending on how many features you want for your register, you can kind of add additional bells and whistles, right? So what if, for example, you want to have a reset? And that way you can, manually reset it. Well, that's actually as simple as, you can see this next line, reg init. So this is a convenience function, inside a chisel library. So I'm giving a default initial value to the register, and that's only applied to register when reset is true. And if you remember what we talked about earlier, right, that reset's implicit, right? So you actually don't even see any mention of the keyword reset in this snippet of code. Basically, whenever there's a reset signal applied in your design, that's going to be applied to this register, and it's going to get that initial value, which in this case is set to be 0. So if I go ahead and, for example, generate Verilog for this, we can now see that, what value our register gets depends on if reset is true or not. Okay, if reset's true, then we're going to set to 0. If reset is false, then we'll set to whatever the input is, right? And, reset doesn't necessarily have to be 0, right? We can make this be a 1, and it'll kind of carry over like that. And in this case, the CAD tools are pretty clever and realize, oh, wait a second, if the default value is 1, I can take advantage of a Boolean identity and ordering things of 1, but ignoring that cleverness, let's kind of revert things for a moment. Okay, so I saw another question coming in. Where is reset? What's reset? Is another signal? Yes. So as we mentioned, that both reset and clock are implicit, so they're in every single module, even if you don't use them, right? So remember last week we had in examples where we were showing our module Verilog, and we were doing purely combinational logic, so you have no need for a clock in purely combinational logic, and yet that was still being there in the emitted Verilog. Like I said, it's there in all chisel modules. Now, before you get worried about inefficient hardware, remember that any reasonable CAD tool, when it sees a unused input or output, it's going to automatically prune that away. That'll not end up in the actual hardware. But when looking at the Verilog right now, yes, it's there, right? And not just there, we actually need it for these state elements, right? Things like registers do need clock and reset to kind of, do what they need to do. And so yes, the clock and reset are passed throughout our design, and they come from external to design, right? So the clock comes from your clock sources, and the reset signal, if you don't do anything, it's the external reset, right? But as I said, there may be scenarios where you want to deliberately reset a module, and you can use syntax to kind of do that. But for now, you can kind of think of that as kind of just the entire world resetting itself, and that's going to be kind of handled by some external thing at the right time. Good questions, yeah. Okay, and then, so that's if you want to reset value. Now, if you want to kind of move up and have one more level of sophistication to your register, maybe you don't want to always update. Maybe you only, take it back. There's so many different kind of flavors here. So, like this is what you need to have in order to have your reg, or what we just showed with the reset. Cool. That's how you could write it. Now you notice it's kind of this 2-line pattern here. I'm kind of to write the input to register, the output to register is 2 separate lines. As a convenience feature, one could kind of combine a lot of this all down into a single line. So wait, how does this work? Well, this convenience function takes in an input. So that's the thing passed in as the input to register. So that's going to be, in place of iota in. So that's kind of doing this functionality. The fact I'm calling reg instantiates a register, so it's like that. And in particular, combination of inputs also includes the ability to do a reset initialization. So that's this, reg init, right? So this is reg next. So yeah, so this single line is, creating a register. It's internally attaching the input we give it to the input.register. It's having a reset value. And because this whole thing creates this chisel register for us, we can now directly assign this to the output, right? So there's no need to have that Scala variable to hold a reference to this because we can just have that go straight over, right? So the point is that, now just different syntax, it's great, right? We're now able to get the register. What was 3 lines is now 1 line. I argue that, a little bit of practice, it becomes very readable. And so it's kind of a nice convenience function. And there we have it. And so you'll see reg next very commonly in your designs, right? Because maybe there's time you want to kind of latch onto a signal and hold it for a cycle. Reg next is great for that. So it kind of handles all of that. Cool. Okay, and then for the final, all the features. Actually, maybe I'll go ahead and generate Verilog for this first. So, with reg next, the internal Verilog looks just kind of like what we had before because we weren't really changing the structure design. It's just convenience features for us as developers to kind of write what we want. But now if we go ahead and use reg enable, that's us adding in the functionality to have a write enable to register. What do we get? Well, now we have this write enable or io.en. And with that, if it's 0, we don't want the value to change. If it's true, we do want to change, right? And so, sorry if I could write that and then rerun it. There we go. So now we can kind of see what we're doing. So yeah, like before, we generate register, just kind of all this semantics for chisel, but you can kind of see deep inside here, right? That, okay, if we're resetting, we get the 0 because we told it, hey, init is 0. If we're not resetting, then we put a new value in there only if the enable is true. If the enable is not true, you see there's no else case inside there, it's not going to change the value. It's going to remember that. It's going to hold that state, right? And so once again, we kind of done that. So if you remember from the prior slide, we kind of showed, hey, with all these bells and whistles, register is kind of like a simple register of 2 muxes, and that's kind of what we've done internally, where those 2 muxes and kind of think of those kind of corresponding to kind of 2 if statements in the Verilog, and that's kind of how that all played out. And so yes, so very often in your Chilla code, maybe you'll use reg, maybe you'll use reg init, reg next, reg enable. There's a few different flavors available in the standard library, but you can use whichever one does, right? And if you feel more comfortable using simpler ones, that's fine. You might need to add some more lines connecting things, but that's okay. Cool. Pause for any more questions. Okay. So, all right, so that's the few different flavors of register. Let's go ahead and put it in an example, right? So first, let's try making a counter, right? So as a reminder, a counter is a hardware block where it holds a number, and when you tell it to, it will increment that number by 1 or perhaps by some arbitrary increment. And then at some point, it's going to reach some sort of max value, and it's going to wrap around or stop counting or something. So in our case, we're making a simple kind of wrapping counter where it's going to count up to the value we give it. In this case, we're saying, hey, max val. And then it's going to kind of handle all that, right? So let's talk our way through this code, right? So what would be inside of a counter? Well, it's going to be a register to hold that count, and it's going to need an adder to add on, the value, right? So if we have count, I want count plus 1. We'll do that. Count plus 1 is going to be an adder. Okay, so then how might this look? Well, we are going to hold our count in a register. So right here, we're doing this with just a vanilla register. Okay, I'll come to the internal in just a moment. All right, so we have our count in a register. Great. And then what do we have? Well, first we need to figure out what the next value should be, right? So normally it's plus 1. But if we need to wrap around, it should be 0, right? And so how do we know if we need to wrap around or not? Well, if the count's less than our maximum value, then we can go plus 1, right? And then if this is false, suggesting the count equals the max value, then we should wrap around to 0. Okay, cool. And then what about the rest? Okay, so then we also have an enable here for whether or not we should be counting, right? Because we don't want to be counting every cycle always. Maybe we'll have a counter a little bit more sophisticated where we have an enable where we can tell it to, when enable is high, it keeps incrementing once per cycle. When enable is low, this holds the value, right? So using this enable, we can do it like this, right? We can say, hey, there is this mux, and yeah, we're gonna, if enable is true, use the next value, otherwise hold the old value, right? And then there'll be times when we need to reset. And so, yes, if you want to reset, you could also use a mux like that. So if you're counting at home, you're saying, wait a second, I ended up with 1, 2, 3 muxes. I use the vanilla register. If I use one of those spiffier registers, could I perhaps reduce the number of muxes? Definitely. But the reason why I wrote it this way is in a few slides, you're going to see me kind of change the code, and it'll make the code transformations more clear if it's always kind of vanilla register and then working with muxes. But here's kind of functionality, right? So here in just a few lines, we've written this in Chisel. We connect our output finally in the end. And cool, we have it, right? And first, go ahead and look at the Verilog. Sure, we can do that too. But I mean, it's not super important. You can see that, yes, there's the kind of thing we recognize. This probably is, the, count plus 1. And then you can kind of see, well, which values get put into the register. Well, if it's reset, it gets 0, right? But if it's, not resetting and enable is high, well, if we're below our max value, we go ahead and put in, this, which is the plus 1. Otherwise, we wrap around. And notice how if enable is low, there's no else case. It just doesn't do anything, doesn't change the value. It holds that value. That's kind of functionality we're going for. Great. Now let's go back to this little bit of trickery here. So what this is, as I said, when we declare a register, we need to tell it the type. And in particular, we're saying, hey, you're going to be holding an unsigned integer, or uint. In this case, we're giving it the width, right? We're saying, hey, here's the width you need to be. And so how big do we need it to be? Well, we're kind of, as a designer, being a little clever and saying, wait a second, we know how big our maximum value is. We need to be able to hold one more than that. So we're going to go ahead and find out how many bits it takes to hold that number, right? So this is log2 ceil, or ceiling, right? So remember, in your rounding modes, you can kind of, normally you can go round down or round up. Log2 ceil, we're going to compute the base 2 logarithm and take the ceiling. This is a very common operation you want to use when you want to figure out a bit width, right? If I have something, I want to know how many bits it needs to hold it, I need to not only just know the log base 2, but the ceiling, right? So for example, if I have 5, I don't care that, the logarithm is like 2 point something. I care that I can't fit that in 2 bits. I need to have 3 bits, right? So I need to like round up. That's what the ceiling's for. And so, yeah, so this is going to figure out and calculate for us that what that width should be. And of course, we need to cast that to a width type. Cool. That's that width inference. So I'm going to finish with this thought about width inference before I answer the question in chat. So here we've given it, based on the max value, it's going to kind of handle things. So I could change the max value, maybe make this, really big. And it's going to, automatically change the widths here and do the right things internally. Doesn't need to be a power of 2. I can make this, 14. And it's going to do the right thing. Now, what happens if I don't give it a width here? Well, it's going to go ahead and do it. We look at how big is our output. It's really small because it doesn't know what we're asking for, right? Now, if I did, perhaps, for example, said, hey, you know what? I wanted to do, an 8-bit output, then yes, it'll go ahead and do this for us. But I argue it's better to, choose to set that width ourselves, right? This is one of those cases where we're doing a little bit of width calculation on our own, but from a code point of view, it's done, I would argue, in a very safe way where we're doing it only in one place, and then the rest of the widths in our design are going to be inferred based on that. So I think this is kind of a graceful, elegant use of that. There was a question in chat, which I think was well answered by another student, but I'll repeat this for the recording, which was asking, hey, wait a second, I went through this effort of having a mux here, And, I had this special case of having a comparator and doing either +1 or 0. Hey, if I add, 1 to 7 and I have a 3-bit binary number, doesn't it automatically roll around to 0? And the answer is yes. Yes, it would. However, if your number is not a power 2, that won't work, right? So if you want to, take that a step further, let's say you want to have a super, super, super optimized counter library, you could definitely imagine, in the Scala, I can probably write this in live time, right? Hey, if max val, which is a Scala thing, mod 2 equals 0. So I use double equals here because this is a Scala comparison. This is me kind of going to town on this. Okay, so like I said, we can use ifs to return things. So I can say, hey, if it's a power of 2, we can say next val is just count +1. And we're using the .u because we need to have a uint. Otherwise, why not do this mux we just talked about, right? So, as pointed out in chat, it's actually not quite power 2, but, if it's +1. So with that change we just did right here, we still get very similar hardware we had before. We still have this +1, we still have this comparison. But now if we make this the thing that's going to wrap perfectly. Oops, I hit next accidentally. Or backwards, I believe. What have I done? I might have. Oh, this somehow got formatted as a markdown slide. Okay, let's get this back on track. Let's get that out of the way. Great, okay. So, and now we can if I click this again, we should be able to scroll. Perfect. Oh, we need to change this to 15. That was the whole point. Great, so now that we change it to 15, you can see, yeah, that comparator is no longer there because when this Scala code is executed, it's taking a different path to hold things, right? So this, at the time the hardware is generated, or Scala program is run, it's evaluating this, right? And it says, hey, wait, max val +1 is a power of 2. Or actually, here I'm doing if it's even. That's actually a bug. Oops, it's embarrassing. It's not actually checking if it's a power of 2. There is an is power of 2 library function. Maybe I'll ask a mode to look in the background and you can tell me what it is. Is that it? No. Okay. But yes, there is a power of 2 function inside the Chisel Standard library that perhaps maybe Mo can look up real quick. But you get the idea. Okay, so assuming I had the right function here, it's going to do just a simple thing. Otherwise, we're going to do the mux, right? So here's a way we can have a little bit of cleverness inside your generator, right? It's able to kind of give any inputs, do some very smart things, right? You can imagine where if you're writing, a simple vanilla Verilog block, you can't quite have this kind of sophistication, right? So already you can kind of see that the generation methodology is allowing us to have more efficient hardware and kind of be more clever. And what's nice is it's kind of hidden from the outside, right? Where the outside user of our module or generator will just say, hey, I give it a max value, connect inputs and outputs, and I'm done. And then internally we can do nice optimizations like we just showed. Now, all of this is to show up me using the muxes, right? And kind of doing it manually. In a second, I'm going to go ahead and shift gears and go use the whens. But this is a wonderful discussion we just had about the bit width inference and kind of alternatives to it. Okay, yeah, the chat conversation looks great, and it's kind of covering what we just covered. Perfect. All right, so here we do with muxes. What if we, simplified that with the reg init? We were talking about, hey, there's more spiffy examples, right? So here we had to, apply a mux at the end for reset. If we use a reg init, we can go ahead and remove one of those muxes, right? Because that mux is kind of secretly internally in a way inside that reg init. Cool. Okay, so we still have a mux determine if we need to wrap around. We still have a mux for the enable, but there we have it. And yeah, I mean, I'll go ahead and generate the Verilog, but it's like the Verilog we saw before, because even though we do different things in the Scala chisel land, in terms of the generated hardware, it's the same, right? We're still saying I want to have register, and I want to have a reset on it. I want to have, these various aspects. So using that reginit made our code a little bit tidier. And it's great. Our wonderful TA has looked it up, and the correct syntax is POW2. And yes, and you can see in this case, hopefully if I were to do this, which would have broken on the prior case, is not going to do the right thing. Actually, 7 is a bad example. Let's do 5. So 5 plus 1 is 6, which is even, but that's not a power 2, so that will need the cleverness to actually do a proper wrap. Cool. Okay, so that's neat. We did a little conversation at class, discussion of the class, and kind of figured out a nicer way to kind of do this. Cool. But okay, so we had 3 muxes originally. Use reginit. We kind of swapped one of those muxes. Our code got a little simpler, a little shorter. We still have 2 muxes left. And okay, what if we use, we could use more muxes, sorry, we could use more sophisticated register contracts to get this lower and lower. I could go ahead and use things like, reg next, or even, and to kind of get it simpler, or reg enable, and I kind of get this very, very simple internally. You know what, maybe I'll go ahead and just do that right now before we get too distracted. So, this is the functionality we have now, but instead we could just say something like, hey, io.out = reg enable. What's our enable? Our enable is io.n, right? What's our initial value? Our initial value is 0. That's what we had from enable, right? And actually, technically, we're going to use this thing here. And actually, forgive me, I need to go back a few slides to remind myself what the order of arguments to reg enable is. It is next, reset, enable, okay. So, okay, in that case, next should be next val, then that complicated thing, then io.enable. And so yeah, we can actually basically boil this whole thing down to the simple line. One wrinkle, in order to write next val, we need count, and it's a little bit tricky to do that without making reference to count. And so you can kind of see why, despite having this kind of functionality, it's really neat. Sometimes it's actually better to leave it as separate values and references. Okay. Yeah, better to leave it alone. But you can still see kind of functionalities of different flavors. So you can kind of see where the most sophisticated register construct available that makes sense for your case can make your code simpler, but sometimes it makes it kind of more cumbersome and awkward, right? And that was an example where I went down this rabbit hole and found out, oh wait, that's not going to be easy to express because I need to kind of refer back to something from earlier. And so this is pretty good. Okay, any more questions so far? Great. Okay, so here we're using muxes, kind of being very explicit. Remember from last time, we also covered this when construct. And we can do the same thing. So when's in chisel, like I said, under the hood, they're going to do muxes, right? And so we can kind of now describe our mux kind of in a very behavioral manner, or sorry, our mux, our counter in a very behavioral manner. We're going to basically say, hey, this takes care of the reset, right? The init function, great. But then if we're not worrying about reset, if enable is true and we're below the max value, then yeah, we should add 1. And if we are at the max value, then of course we're going to wrap around. And so this is kind of perhaps a very, behavioral way of writing this. We know that under the hood, that chisel compiler is going to do some analysis and figure out how to add muxes and make this kind of combination of things happen. But this is it, right? And so in terms of the hardware we get, this should actually look very similar to what we just saw, because, it's, going to produce the same things internally. Now, one thing I want to point out, be really clear about, I deliberately introduced this when construct last Friday during the conventional logic lecture. And the reason why is when has nothing to do with time or state, right? when is simply, when a condition is true due to internal blocks, right? And things we're doing internally in this case is we are, performing a chisel connection, right? So this connection happens conditionally based on this, right? And so as we know in hardware, we turn conditions into hardware, that turns into muxes. Chisel compiler does that for us. In this case, we have whens that are operating on chisel components that happen to include registers, right? A register is not treated specially. It's another chisel component. We just happen to, using when to control which inputs and outputs are connected to the registers in which way, right? In particular, what we're saying is, hey, we have this register count, and we are using these when statements to control what input it gets, right? So register's input is either count plus 1, 0, or actually, believe it or not, none of these, meaning it's going to be left alone, right? It's going to hold its original value. Okay. Cool. Questions on this? Okay, see some comments in chat saying people saying they like this when syntax. Yes, it sometimes is perhaps maybe more readable. See another question coming in. Should we think of when statements like Verilog's always blocks? Sort of. I'm a little uncomfortable with that for a couple reasons. It's one of these things where you can kind of find places where they're similar and places where they're different. An always block in Verilog can be used to infer state elements, right? So remember in Verilog, usually you don't explicitly say you want a register. You kind of use a always block in a very deliberate way to infer a register, how the tools infer it for you. So in that sense, I'm a little bit nervous about comparing when to always, because really when's about connections and not about state elements necessarily. On the other hand, you can use always blocks in Verilog even without registers, right? You can have an always and use that to do combinational logic. And in that case, it is kind of similar. To be honest, the when in Chisel, I would say, is more similar to actually the if in Verilog, right? So Verilog has an if when you're inside of an always block, and to me, that's a much better analogy, right? The always block is kind of, for those who don't know Verilog, what the always block says is, hey, there's some conditions. So whenever this evaluates to evaluate this assignment list, do the internals, right? So for a flip-flop or register, right, you only want to change once per cycle. So the way you do that is you tell, hey, when the clock edge is on this positive edge, do this inference and it infers the register. You're not required to have positive clock in here, right? You can also have arbitrary signals in there, and then in which case it's going to evaluate at other times, and you can even do pure combinational logic with always, right? So yeah, always is complicated. I don't want to perhaps get too deep down to Verilog details of this course. It's not what this course is about, but to kind of summarize, I would say the when in Chisel is more similar to a Verilog if than an always. But yeah, good question. But yeah, really what I want you to think about when you think about Chisel is rather than worrying about all these constructs, think more about, okay, I'm trying to build this hardware design. So imagine I have this block, I have this other block, connect them together, right? So all you're doing is instantiating things and connecting things. And there's just some nice features in the language to make it easier for us to kind of express these things, right? Where rather than having to say, I want thing A, thing B, here's a mux to choose between them, I can say, you know what? I'm going to use a when block, a when to kind of, do that in perhaps a more readable, more graceful way. Cool. Yeah, good questions. And so just a moment ago, you heard me talking about, hey, well, what if I wanted to use reg enable? Well, if I, verbosely kind of reuse a circular reference to myself, I can, and I kind of jam a mux in there for next val. Remember the problem I had previously was I couldn't write the next val line because I needed a reference to count. Well, if I do that internally, I can. This is one big long line. So on the one hand, you're saying, hey, wait, I have a single line module body. Isn't that great? If I go ahead and evaluate this, same block we've been seeing before, same hardware functionality, less than the chisel, all done, right? I would push back on that, right? Remember, one of my themes for this course is consider readability. I think if I was to be handed this block out of nowhere, there's kind of a lot going on here, right? This is one line, I'm going to spend, some amount of time parsing as I'm a human, thinking about what's going on here, what's going, and then, especially when you have very large things inside of argument lists, to kind of remember where the parentheses end, use your ID to kind of point out, oh yes, this turned green, so it goes from here to here, great. It's a lot of work, right? I would argue this prior expression gets the idea across pretty clearly, right? Where I can say, hey, if it's enable, you're doing this stuff. So I would argue, even this other one's more lines. What is more lines? If it's, to me, easier to read, easier to maintain, easier to understand code, right? Where, for example, we just discussed earlier, where what if I want to have this optimization where I can recognize if the numbers have certain conditions and, remove the need for a comparator by, handling using natural wrapping ability. It's in the optimization. With this expression, you can imagine me kind of, changing those few lines right here to make that happen, right? However, if I was using this expression, I basically kind of need to start over, right? And you kind of say, okay, well, I have this one complicated line, and I have this other complicated line of if wrapped around all that. So, yeah, I would argue that in this particular case, this perhaps went a step too far trying to minimize, and I think that this other thing would be more readable. There's a little bit of subjectiveness to this kind of conversation, but I think from the more you kind of do this, the more you talk to other people, the more you get feedback, the more you read code. I think the more you kind of develop your own intuition for this kind of stuff. Okay, questions. This has been a great conversation. I'm appreciative of your guys' questions. So as you can see, what we've been doing so far is just using register, showing examples of these convenience features in Chisel to kind of have more sophisticated registers, showing muxes versus whens, playing around with different designs, talking about readability, kind of all packed together. Okay, so let's go ahead and shift gears then and test out our counter. So remember from before, we had this, to write a test is actually pretty simple. We didn't actually talk about this line by line, but we can do it now. What do we do? Well, this is actually using this Chisel test library under the hood. We can say, hey, I want to instantiate an instance, right? In this case, a counter of, maximum value is 3. We'll come to this little syntax wrinkles in just a second. In the future lecture. But basically, we're taking the instance and using it, right? Because we have our counter instance we're testing, C. And what are we doing with it? Well, remember we have peek and poke, right? In particular, I want to poke an input to it. So I want to say, hey, set the input enable to 1. And then I'm also going to check the output, right? Hey, what's the output? Well, because we're having just reset the thing, we expect it to be 0. Now, this is what we covered. We saw this in an example on Wednesday and Friday. The wrinkle that's new here is this step function, right? So what does .step do? That advances time by 1 cycle in the simulation, right? So these lines in your test bench, they're evaluated in order because it's the Scala program that's executing, and they're applied in order. So if I do a peek and a poke or whatever, that'll happen in order. But in terms of the time that's passed in the simulation, there's not really any cycles going by. If you want a cycle to advance, you need to say .step. Okay, so the first cycle, we just turn the thing on, we expect it to be 0. The next cycle, we still have 1 being poked in, but now we expect it to be 1. The counter should have advanced, right? And okay, the next cycle it's going to be counter should be 2. It's advancing. Then 3, it's at the maximum value. But what happens? Well, we're actually turning off the enable. So then in the next cycle, we're going to see it's still 3. And then to close out, we'll go ahead and turn enable back on and watch it wrap around. And so this is our little example. And I might have broken this by messing around with our test benches too much. So let's go ahead and instantiate this particular flavor of the counter. Great. And then this should work again. You can see the different versions have slightly different I/O port sizes. And yes, it works, right? Great. The question is, do I need to call poke every single cycle? No. No, you do not need to call poke every single cycle. Basically, whenever you poke a value, it's going to keep poking that value until you tell it otherwise. So yeah, I could, just as well, because I was poking 1, I could have, not had these lines as well as those lines, right? This should also get the same result. Sometimes, when we're running a test bench, it's a little bit easier to kind of just have all the signals there. It depends on the test bench, right? Where if you have all the signals every cycle, it can be very verbose, very long, a little tedious to read and write. However, sometimes it makes it really easy to kind of quickly change things. Or if I want to go ahead and change a value or do stuff. So if you look at my own test benches, I kind of do both styles, where some styles I have every signal, every cycle to kind of be very clear what I'm doing. Other times I do just only record them when they go through it. The question is, why does it say 0 tests passed? We didn't make a proper test case. So test is kind of some very convenient little shorthand to kind of get us off and running. If we're actually doing the proper testing stuff, we actually have to like instantiate a little more boilerplate code and like name the test and that kind of stuff. And then we have like a properly named test and with a description and that kind of stuff, then it'll actually start counting. But in this case, because we're doing things quickly inside the interpreter just to get running, and we're trying to minimize the amount of boilerplate so we can kind of, maximize screen real estate. Yeah, I guess in this case, there's some, cute bug here or, quirk where it doesn't actually register as a test. But yes, it did run. If I was to do something wrong here, it will tell us we did something wrong. And it's going to tell us, oh, wait, you got the wrong thing. It didn't get the value you expected to get. We'll be talking about testing a lot more, I believe, on Wednesday or Friday. I forgot my own schedule. Forgive me. Just a moment. From before, yeah, I believe it will be it's going to be this week is the answer. Sorry, I'm too curious to know. Testing's probably going to be... testing is not till next week, but we'll keep making more sophisticated tests kind of on the way implicitly, and then we'll have a very proper big-time testing lecture next week. This week we're talking about collections and encapsulation, so getting more and more modularity to our design for the rest of the week. Okay, cool. So we wrote our test, we wrote our module, we had different ways. We talked a little bit about ways of expressing it, tested it, it worked. Cool. For now, you can kind of treat a lot of stuff a little bit as like boilerplate, and we'll kind of make it less boilerplatey as we get more familiar with it. All right. Questions on this so far? Okay. What else is there? Well, Chisel has a Enum construct. This is an enumerated type. So sometimes you want to have nice human readable names, and you want to let the tools worry about actually assigning numbers to that and working with it. So the way to do that is with Chisel Enum. For now, you can treat this as kind of magic syntax. So you kind of give the names you want on one side of the equal sign, use these double colons, and then you will get an enum. Okay, and so why would we want enums? The most common cases are things like I want to do a state machine, but maybe you also want to do things like labeling ways in your muxes, where you can say, rather than mux way 0, 1, 2, 3, you can say, oh, you can actually better annotate your code and explain, I want to select this way. This is the count plus 1 path as opposed to the wraparound path, right? Or other times you have, interfaces between modules. And yes, in the actual hardware, it's going to be, numbers going over wires, but, to make your code more readable, maybe you want to have those be labeled, right? So rather than doing operation 2, you want to know I'm doing operation, send packet or something like that. You don't want to label that. And so enum's pretty cool. You can see in the slides listed as experimental. It'll become not experimental very soon once the next version of Chisel is released. But it's already available in the version we're using in this course, and so you will be using it plenty. Cool. So let's go ahead and put that to work. How are we going to use that? Well, we're going to go ahead and make a state machine. So remember, finite state machines, these are a way of kind of capturing how something kind of moves between states. So the way they work is you have a state you are in, represented by a circle, and that has certain, actions or outputs associated with it. And then if you receive an input, that's one of these labels on a line arrow, you then, go to the next state depending on whatever conditions are met, if they are met. So, doing one of our favorite critters here in Santa Cruz, we have the raccoon. So you can imagine, maybe on default, raccoon, what's it doing? It's hiding, right? If it's at nighttime, doesn't hear any noise, maybe it's going to go change out and wander, right? And when wandering, if it comes across some trash, great. It's like a rummaging into trash. And then if it finds some food, perfect. It can eat. And if it eats all the food, there's no more food left. Then it's going to go back to wandering. If at any point we hear a noise, time to hide, right? If you're wandering, if you're rummaging, if you're eating, going back to hide. So this is a tiny, 4-state machine example. You can imagine other sorts of ones, but this is what we're trying to build, right? Okay, so this functionality is what we're trying to build. In this case, we're using a, fun animal, but, often in hardware you have, I have initialization state, a processing state, a busy waiting state, et cetera. This is very common. So how might I write that in Chisel? Well, we can write this state machine using when statements, right? So I could say, hey, let's give names to our states. So rather than writing state with 0, state 1, state 2, state 3, let's use that Chisel enum. So I have my states, hide, wander, rummage, eat. If you go back to the prior slide, what's the big picture interface for this state machine? Well, there's the action you're performing, such as, hide, wander, eat, rummage. That's the current state. But then there's these inputs, right? Things like noise, food, trash. Those are inputs to our state machine, right? And then what's our action or output? Well, that's kind of our state in this case. So the state and the output is kind of the same thing, right? So you can kind of see your action. Well, really we're just assigning our action to be our state, but okay. So what do we do? Well, if our state, for example, if we're in the hiding state and we don't hear noise, then we want state to become wander, right? So we can kind of go back to the prior slide and we can see that, right? Okay, if I'm in hide and I don't hear noise, next state is wander. If noticed it, there's no other else ones for this particular issue, right? So if I'm in hide and this is not satisfied, it's going to stay in hide, right? If there is noise, it's not written, but it's going to stay in hide because, that connection was not made. The connection of state to wander was not made, so state still holds the connection it had originally. And so it's going to keep holding that connection, right? Likewise, okay, if I'm in wander state and I hear noise, I go back to hide, but if I don't go back to hide and there is trash there, that's the else when clause, right? I can go ahead and go to state rummage, right? So that's that functionality we saw in that next one, right? So here, if I'm in wander and I hear noise, I go back to hide. And if I find trash, I go to rummage, right? And so you can see we kind of took that state machine and mapped it out to whens and else whens. Can be a really nice, clean way of doing this sometimes. And you can kind of see the whole thing written out here, right? So I'm going to go ahead and look at the Verilog. The Verilog is not going to be as illustrative as before is because you can see some of these IO names are great. They're very readable, but then our enums, right, were turned into numbers, right? And so those numbers are now inside of here, and you can see that combination of whens and else whens is a combination of ifs and else ifs inside the Verilog. But for now, I would word less with the Verilog and more about this kind of chisel, where here we have our state machine. We've kind of captured this cute little animal's behavior in a certain way. So maybe I'll pause for any questions on this so far. Cool. Okay. So here we're doing it kind of with when. And I was kind of telling you to think a little bit about like when it's kind of like it's conditional. So, in other languages, and when you get too many if statements, you have a switch statement. And so does chisel, right? So if instead maybe you find this to be a more clear way of writing it, same IO, same enum for states, still using a register to hold our state, and, defaulting it to hide, right? That's what the initial state was before. But now we're switching on state. So rather than this kind of combination we had before of, when state equals this, else when state equals this, else when state is this. Remember, because we're doing chisel comparisons, these are triple equals. Here we're doing that as a switch statement, right? So based on state, if it's hide, wander, rummage, or eat, we kind of have these blocks. So it's a little bit of kind of interesting embedded DSL language syntax here where we're switching on state and then doing is in these cases for each of these kind of cases, kind of almost like case in a way. All right, well, if we're in hide, we have that internal when. So we kind of took the top level when, else when chain and turned that into these switch statement to kind of clean up a little bit. So maybe this is a little bit cleaner, right? Rather than having to do state equals wander, we just say is wander. In terms of what hardware produces, this should be exactly the same as what we just saw in the prior slide. The enums still get turned into numbers, and the switch statement still turns into ifs and else ifs inside the Verilog. But this is another way of expressing it. Okay, I'll pause for any questions on this so far. Great. Okay, so then we've covered quite a bit of stuff today's lecture, so don't worry, we're almost done. Let's go ahead and test this thing out, right? So testing a state machine should deserve a whole lecture on its own, right? Because you can imagine now this internal state, I need to think about what combination of paths that would take. In this particular case, I chose one combination of paths where I said, hey, what if I imagine a particular execution where I'm going to, as a human, look at my intended state diagram and, pick a traversal and go here and through here and try to get through as many of these arrows as I can manually, right? So this isn't a very scalable approach, but it works fine for today's lecture where I say, hey, okay, well, let's say initially there's only going to be noise. And so I want it to stay inside of 0. And we're assuming in this case state 0 is the hide state, right? And then if there's no more noise and we advance the time with the step, then we expect to move on to state 1, which was that, wandering state. And then, let's go ahead and say, oh, yes, there actually is trash. Then we expect it to go on to the next state. Then we say that trash is gone, but we're in the food. We can kind of keep moving through the states. So here we're kind of manually tracing through the states. For very simple state machines, this is perhaps very reasonable. Next week we can cover testing. We can cover some perhaps more sophisticated ways to kind of deal with these state machines and testing them. It's a whole other topic, but these simple constructs of, poke and step and expect gets a lot of the way there for kind of creating these tests. I personally, as a human, have a convention of liking to, put new lines that kind of distinguish behaviors across cycles or like mini test cases, right? Typically, you might have step on the last line of a block, but I chose to kind of see the results of the prior interaction. So I want to see how it changes the output. That's why I put the expect for the state right away. Cool. Okay, so that was that. But now that we've built our module, we've written some test cases. What if I'm, trying to play with this thing and see more about it, right? Because so far, what have we done with our modules? We've been making modules, and we've either been looking at the Verilog to kind of be aware of what hardware is inside there, or we've been simulating them. In particular, we've been simulating them with test benches, right? So these test cases, in order for test cases to actually run, it's actually, instantiating the hardware in a simulation and actually executing through it. And these lines in our test bench are, commands being issued in that simulation, right? And so we're telling the simulation, hey, simulator, put this value on this input, advance time, or looking at the simulation output, hey, I want to say it doesn't, I added actions out equals this, right? But these test benches are essentially simulations, right? Since we're doing a simulation, you can do simulation for a variety of things. You can do simulation specifically for testing. You can do simulation more generally. You can do simulation for debugging. You can do simulation for development. You can do simulation a lot of different times. And so when you're simulating, you have a few choices, right? So when you're using a test bench, like you just were using, you can manually set the inputs, you can manually check the outputs, you can do stuff with that. However, if you're just simulating in general, especially outside of a test, you may also want to do other things, right? You may want to, for example, print things, right? Now, printing at first might seem like a very weird thing to do because, wait a second, what does a print mean in hardware? Well, guess what? There is no print in the hardware, right? The hardware is the hardware blocks instantiated, but if you're talking about simulation only, yes, you can, inside your simulation, set up such that there's a print statement that happens under certain conditions. And you can print out values and look at them. Much more common for hardware designers, which we're familiar, of course, are waveforms, right? So waveforms are a way you can see visually all the values of your design over time. And it makes it very easy to kind of debug things and go through it. And so the waveform format Chilla produces something called VCD. And I'll demo that in just a second. And you can go ahead and see the values of your design. Now, haven't taught this class one time before. I kind of, learn from what students like the best and what they do. I think a lot of students, once they see Printf, that's very familiar to them. They do Printf in software languages and they can go ahead and do that. You can go pretty far that way. But eventually it's going to get really onerous. And, what happens is you print some things and then you're in a simulation, you read the output and you go, oh, shoot, I wish I'd print this other thing under these different conditions. And so you end up kind of continually rerunning things, right? And, changing your print statements, rerunning, change your print statements, rerun. You can get by that way. I don't recommend it, but you can. Until your design gets beyond a certain size. And at what point you can't do it anymore, right? So for very small designs, the time it takes to synthesize your design, print it out, and to look at it is pretty small, right? So that's fine. But as your design gets bigger, you're not going to want to go through that loop because it takes, seconds, minutes, or hours for your design to re-simulate itself. You're going to rather want to simulate it once and kind of go through it. So that's kind of the beauty of a waveform, is you kind of run a simulation once, you get all the data once, and then you kind of, as you have more questions about, oh, I'm curious about the value of this signal at this time, you can just go answer that from the same waveform. But, depending on your style and what you're doing, you can use both in this class. I recommend using waveforms if you haven't before, just to get a play around with them. They're good. And but both prints and waveforms, I think, are really helpful, but I haven't emphasized on the slide, only for debugging, right? I think it's very common for people to try to use them for testing too. Like, oh, if the output on this line, my code is 4, I know I got it right. If it's not 4, I know I didn't get it right. Don't do that, right? Because then nobody else can use your test, right? You want your test to be automated. You want us to have, pass, fail. You want to see that, thing coming out the other end. Same thing for waveform. You don't want somebody to say, is my module correct? Well, just run it, open the waveform, and look at, this time cycle, what value is there. No, that's not a test. That's just a simulation, right? So to me, tests need to include some amount of automation, let you know if you have the right answer or not. And so prints and waveforms are great for debugging, and we're going to cover them in just a second, but do not use them for testing. Testing should be like a proper test bench. And fortunately, we have chisel test, which is great, and so we'll just use that. Okay, so for printing, actually, no, I'll do the waveform first. So to go back a few slides, you may recognize that I had a line commented out. So even in these notebook environments, you can do waveforms. So what is this doing? This is just a little bit of a hint to the simulator saying, you know what? I want you to save the waveform. And we're going to have this turned on by default for the homeworks, which are going to be non-Jupyter notebooks. And so you don't even need to do this. So you're going to get a waveform. Okay. So when you have that waveform, what can you do with it? Well, I hope to have the other window. So I already saved that file. And so yeah, so now I'm inside a waveform viewer. This program is called Sequential. It's a VCT viewer for Mac OS. We recommend something called GTK-Wave, which is a very portable tool. It's available for Linux, Windows, Mac. But let's say here I'm using Scansion. So yeah, I can go ahead and drop in my signals. There's my account. Oh, sorry, the clock. I can drop in reset. You can see initially reset is 1. That's done automatically by the test bench. And perhaps maybe this is looking at the case of my counter being run. What is the input, the enable, what is the output? Okay, cool. And you can see, oh yes, at this time in the simulation, I can see that, yeah, I had a certain value, and you can see how that kind of plays out. Cool. So I can see, oh yes, at this time in simulation, enable was 1, I had the value of 2 in my count. And yes, and this is why it's nice in the waveform. I go digging in, I say, oh, hey, wait, okay, so I had, what was the value of that register? It was 2. What was the next value going to be? The next value was going to be 3. You can kind of see the various parts and debugging what's going on. So I really, really recommend waveforms. GTK Wave is kind of the most common way of doing it. There is a way, if you use VS Code, to actually use a plugin in VS Code to get waveforms inside of there. So a lot of students like that for their projects and their homeworks. Recommend that. We put some of these resources on the course homepage. We want to learn about how to install these tools and use these tools. Okay. Then coming back to the printing. So, let's go to the very end. For printing, you probably seen this already in Scala. There's something called print line. So yeah, that just prints the current thing. It does have what's called string interpolation. You see this in other languages where you can just put the variable followed by a $sign and to get it to include there, or you can do an expression, right? Or if I want to evaluate something, if I want to evaluate something, I need to put inside square braces or curly braces, right? So I can go ahead and say, hey, I have a value 4, and hey, I can, print it and even say, some attribute of that and get the class, right? Cool. So that's printing in Scala, which is something you should do while you're generating your hardware, right? So if you want to say, hey, I did the optimization we discussed earlier, where I recognized, I can do the wraparound without a comparator because, I'm 1 less than a power of 2. You can have a print line that says, hey, I did the optimization. Great. So print lines are for Scala. If you're in simulation, then you need to use Printf. So Printf is not inside Scala normally. It's something that was added by Chisel. For printf, you can do it either C style, where you have, the string including, these delimiters, and then you pass the arguments afterwards. Or you can do it interpolation style, which is kind of nice. You can say, hey, the value is, $myval. Under the hood, the compiler will do kind of the right thing. So here's our counter again. And one nice thing about having a kind of this when organization to your code is, hey, if I want to go in and drop into printf here, it's not too hard for me to do, right? With that complicated one-liner, this wouldn't be so easy to do. But hey, with this one statement, I can kind of just slip this in here. So I can go ahead and drop these printfs in here. And then reevaluate this so that it knows what it is. And then if I look at the simulation, in this case, I'm just going to run the test really simply. Hey, I'm going to, poke one to the enable and then advance some cycles. And you can see, yes, here's, the printf running, right? Now, worth remembering that these printfs are not in the hardware, right? These are something that's being done in simulation only. Real hardware doesn't have a printf, but for debugging and development, it's going to be very helpful. So printfs are great for, like I said, for debugging. They should not be used for testing. Testing, you should use test benches. Waveforms are also great for debugging. And there's a couple more slides, but I'll save those for next time. Any closing questions? Oh, before I forget, I will do the administrative reminder that yes, lab was posted over the weekend. You'll be submitting those Jupyter files via Gradescope. And then the delay was getting the autograder set up. Hopefully in a few hours that'll be live, so you can just complete the lab however you do it, whether it be locally or in that binder instance. Upload that file to Gradescope, and then from Gradescope, you will be able to eventually, at some amount of time, it'll give you the results so you can know your score before the deadline. If you want to, go ahead and see if you have a bug and fix it and rerun it, you should be able to do that. Cool. All right. Have a good day, folks.